3D. Now, sadly, that animation probably took me about an hour. So let's watch it again. Dun dun dun. 3D. Okay. When we go into the third dimension, we're going to add the third dimension, and basically nothing changes. Okay, all the things are still true, but now we have an additional third dimension. Okay, so if you know the angles between the forces and axes, resolving forces is easy. Okay, so we want to talk about the f of x, fy, fc. Now remember before we talked f of x is f cosine theta and fy is f sine theta. Well, now we're going to define theta a little bit differently. You'll notice that these say theta x, theta y, theta z. Well, what are those? Okay, so we're saying that the x component of this force, so you have this force in 3 dimensions, right? A portion of that is along the x-axis. Well, the x component of the force is f times cosine theta x. That theta x is in the plane between this vector and this vector. So it's one of those things that it's true and it's nice to know, but it's not overly helpful because generally speaking, you're not going to have that angle. And it's true for fy and fc. They're all f cosine theta y, f cosine theta z. So these things are absolutely true, but you generally don't have this angle. You'd maybe know from here in this xz plane what it is to the projection, and that's not the same thing. Okay, also these angles, these theta x, y, and z, are not completely independent. So once 2 of them are defined, the third is actually also defined by cosine squared of theta x plus cosine squared theta y plus cosine squared theta z is equal to 1. And that's because really you only have 2 independent angles. The third is just breaking down the second angle into components. Okay, so here's a little trick. I say a little trick, but this is the basis for much of what we're going to do. We're going to come back and do this over and over. We'll do this in class. This is one of those things that is very important that we understand how to do this. In order to solve a common problem, okay, when a force is defined by its magnitude in 2 known points along its line of action, okay, an example of this is a rope. Picture a rope. You have a rope tied between, say, 2 points. A rope isn't capable of pulling this point in this direction over here. It can only pull it towards in the direction of the rope, right? So you know the direction that it's going, you just don't necessarily know the magnitude that it's going. So we want to define the force vector F with the following steps. So we want to define that there's some force vector in this rope, say going from here to here. Well, how do we do that? Okay, first step, define D as a vector between the 2 points. So there's a point here, there's a point here. We're going to define D as this whole vector, okay? Now, how do we do that? Well, it's simply x2 minus x1, y2 minus y1, z2 minus z1, right? That's the x component, the y component, and z component. And then what we're going to do, we're going to calculate the magnitude of D. So the magnitude of D is, we're just going to call D, right? And it's the sum of the squares. It's the square of the sum of the squares, right? So dx squared plus dy squared plus dz squared, quantity squared, square root, sorry. So the magnitude of the D. So why do we want to know that? Because we're trying to find the unit vector in the direction of D. So lambda is what? We already talked about this. Lambda is a unit vector, and it tells you, it gives you a direction, and it has a magnitude of 1. Okay, so D has a magnitude of not just 1, right? This can be anything. It can be 10 feet, it can be 372 feet, it can be 0.01 feet, right? It can be anything. But it has a direction and a magnitude. So we're going to take this vector and we're going to divide by its magnitude, and then the magnitudes will cancel out and we'll just have the direction. So lambda is this vector, so the x component, the y, and the z component in their respective directions divided by the magnitude. Okay, why do we want to do that? Because what's special about D? D is a vector from here to here. Well, that happens to be, and it's not just dumb luck, it's because that's what we're doing, it's in the same direction as the force, right? Again, because cables can't provide forces in anything other than the direction that they're pointing. And so we are going to say that we're going to define our force vector F by the magnitude of the force. That's F, you know, so this is bold and this is not bold. So the force vector is the magnitude of the force times the direction. Remember, because we can multiply, this has a magnitude of 1, but a direction. This has a magnitude, but not a direction, so we can combine these two. And now we have the magnitude of the force and the direction of the force. And this is going to be something we're going to do over and over and over throughout the semester. So please take a moment to understand this, practice it. We'll do examples of this in class as well. Okay, this is definitely worthy of an example. So let's do a couple examples of this actually. Let's do example 2.7 and 2.9.